Hi, this is Dr. Shane, and this is the podcast of Triple R's Einstein A Go-Go, a weekly radio show exploring the wonders of science and its impact on the world, broadcast live on Triple R from Melbourne, Australia, every Sunday. Hope you enjoy the podcast, and feel free to get in touch with us via Einstein A Go-Go's Twitter account or Facebook page. Good morning, everybody, and welcome to another episode of Einstein A Go-Go. I'm Dr. Shane. Thanks so much for tuning in to Triple R for an hour of science. We've got a huge show prepared for you today. I think we're going to start off in Oxford in the UK, then we're heading back to Melbourne, and then we're going to head over to New Zealand with a range of guests, which I hope you thoroughly enjoy. There's some really good, excellent science communicators coming on, so that's going to be a lot of fun. So I'm going to throw to a quick announcement from the station, and then when we come back, we'll be in Oxford, hopefully, if all goes well.
Triple R on FM, digital, online, and via the app.
We're joined now by Dr. Susie Shi from the University of Oxford and the University of Melbourne's physics departments. Good to see you again, Susie. Good to have you back on the show.
Good to see you as well. Thanks, Shane. Thanks for having me.
Now, you, a few months back, took an extraordinary decision to head back over to the UK, where you're sitting currently now in quarantine, and we'll talk about that in a moment. But what possessed you to leave Melbourne and head over back to Oxford?
So a couple of reasons. So I have this slightly strange setup for the last couple of years where I've been joint between the two universities in some capacity. So my sabbatical period was actually coming to an end in Melbourne. And so I actually had to come back over to the Oxford side, but specifically because of my research fellowship here and the research that I'm doing here. And finally my lab had reopened over here. So it was kind of time to come back over and push things forward, because we've lost about 18 months of progress really with the labs being closed. So I was fully vaccinated when I left, and obviously that was a calculated risk to take to come back over.
Yeah. Do you still have a lot of students in the UK that you're managing, or early career researchers and so forth? What's it like over there?
Yeah, so I still have 3 PhD students over here actually, and obviously I've set them all up with co-supervisors, but they're all going into they've just started their 3rd year of PhD, so hopefully most of them will finish in 2022.
Yep.
But of course, again, especially with one of them, because the experiment's been delayed. Well, he's done a lot of simulation work instead, but we hope, we hope everything will get finalised next year. In which case, my workload over here will be a lot lower, and then I'll become just visiting lecturer over here instead of actually trying to hold down 2 academic jobs, which is a bit much. Yeah,
a bit much. How did the students react when you must have walked in one day and said, "Hey, I'm the Southern Hemisphere. That's where I'm heading. Catch you later."
Yeah. So actually, these 3 students, when they started, I was transparent with them about that in the recruitment process, and that's why we set them all up with co-supervisors and embedded them in research groups where they could have good interaction even when I'm not here. But that said, I'd already gotten used to I was early in the sort of Zoom culture, right, because of this back and forth. So my groups on both sides were used to having Zoom group meetings well before the pandemic, just because I was traveling and on the wrong time zone. So they kind of came into it with open eyes, which I'm grateful for, because it would never be nice to come into a PhD and then suddenly discover that your supervisor is going to be going literally to the other side of the world.
Yeah, that'd be a bit tough. Now, here in Australia, we're just starting to, universities are reopening. There's even the hint that international students will be coming back onto campuses, which is amazing. And to be fair, not just for the money, but because they bring a lot with them beyond that, which changes the way our universities look. What's it looking like at the moment in the UK? Because obviously the freedoms there have been very different to what we've experienced here in Australia.
Yeah, so I guess we've really gotten to sort of COVID normal over here, or living with COVID as normal. The universities have gone back to operating in person. There are obviously still some restrictions in place, and those are put in place by the colleges and the university. So for example, in my department in physics here in Oxford, I actually wasn't allowed to use my office just for office work. until October, even though all the restrictions lifted in roughly July. So most workplaces have been managing it based on individual risk and local case rate, things like this. But Oxford have actually been very good with their early testing service. We've got all the lateral flow tests available for free all the time, and it's felt quite safe, surprisingly, given the case rate. But that was just for me a matter of, the first few weeks when I came back over in August, I really was terrified because, of course, this is before the recent wave that happened in Melbourne. And so I literally went from zero COVID to 30,000 cases a day. And the psychology of that was quite challenging. But really, it was a matter of going to a few small things. And then, you have your first COVID scare where you texted the next day and told, oh, someone there has tested positive, and then you freak out and you do all your lateral flow tests and things, and then about 5 days later you reassure yourself, okay, no, I'm vaccinated, and so I haven't picked it up. It's managed to protect me. So over time, that helped me, at least psychologically, to get the confidence to get back out there doing things. But I have to say, I'm still doing mostly outdoor and mostly small things, and we've also sort of set up with friends of mine and colleagues of mine sometimes additional protocols that we've put in place ourselves. So, for example, I have one group of friends where when we hold parties, particularly because it's a party, it's close contact, right? We all do a lateral flow test and post it to the WhatsApp group before we arrive. So we've sort of created our own normal.
Yeah, look, I mean and that's a spectacularly smart way to go, because at least then you also walk in some confidence that you're safe and that you'll be okay. And none of these things are perfect, but every sort of layer that we add makes things a little bit better, I think. Now, for those of our audience who didn't hear our last interview, which was some months ago now, just give us a little bit about your research and what you're up to over there in the UK at the moment.
Yeah, sure. So my research is in a field called accelerator physics. So it's kind of related to particle physics, which is exploring the fundamental constituents and forces of the universe. And that's kind of where I started. But I actually shifted over into working on the physics of the particle accelerators themselves. So there's many, many different uses of particle accelerators, which we can talk a lot more about. There's about 50,000 of them in the world. So not all of them are these gigantic ones like the Large Hadron Collider. But my research over here in the UK actually focuses mostly on what we call high intensity hadron beams. So that is usually beams of protons, like we have at the Large Hadron Collider. You'll recognize the word. And the aim of the game is basically to try and get as many protons as possible into a beam. And that might just sound like a bit of a game, but it's sort of a different challenge to the very high energy that people are going for in some experiments with these very high energy collisions. Instead, when you're looking at having a very high intensity of a beam or lots and lots of protons in one small area, there's different challenges, but it's just as important, because if you think about a collision between particles that's going to produce data that's going to help you find Higgs bosons or whatever else might come next, there's multiple factors that go into that. The energy is one of those, but actually the number of collisions is also very important. And so actually increasing the number of particles in the beams is actually part of what's just happened in the upgrade process to the Large Hadron Collider, what they call the high luminosity upgrade. High luminosity is shorthand for increasing how many collisions you can get, right? So my experiment over here is actually a scaled down experiment. It's actually not a particle accelerator at all, but it can mimic one in the lab. And with that experiment, what we're working on is trying to understand how these very intense beams behave and how we might be able to design new accelerators in the future that are fundamentally designed from the ground up to handle these very high intensity beams. So there's a couple of issues with these high intensity beams. When you get charged particles all in one space together, they don't ignore each other, right? They're charged, they're electrically charged, and so they actually interact with one another. Now, at low energy, that interaction is a repulsion, like we learned in primary school, high school, that electrical charges repel each other if they're the same type of charge. Actually, once you get up to high energy, there's additional effects, which mean there's both attraction and repulsion between different parts of the beam. And it gets to be a very complex process because it's also then interacting with the beam pipe around it, with the magnets around it. It's just a complete electromagnetic mess, basically. And so our job as accelerator physicists is to really understand the dynamics of what's happening with that, and to try and avoid losing these particles. Because if you lose even 1 in a million particles in the Large Hadron Collider, you're going to drill a hole in the side of the beam pipe and destroy the machine. So this is a high precision game. Yeah.
Yeah. And I suppose a lot of this also, mindful, we only have a few minutes, but a lot of it comes back to issues, as you said, of all those other different applications as well. And many of those would require miniaturization and sort of better efficiencies. And so being able to produce all these different types of beams in a more controlled way would presumably play into a lot of that, especially in medical devices and so forth.
Yeah, that's right. So there's benefits sort of across the board, right from that sort of fundamental collider physics all the way into what's happening in hospitals. And actually, there's a really interesting confluence at the moment of my work in the medical area and this work in the high intensity area, which have until now been separate in my career. But actually, recently it's been discovered that if you deliver radiation for therapy, for cancer therapy and radiotherapy, or proton beam therapy, if you deliver that very quickly, so a few milliseconds, even up to maybe 100 milliseconds, then it has what's called the flash effect on tissue. So the idea with radiation therapy is you try and kill cancer cells and keep healthy tissue unharmed, right? And this very rapid delivery appears biologically to have an increased killing effect on the tumor cells and a decreased harmful effect on the normal cells. And so people are now shifting toward this question of, well, our current technology can't deliver beam that quickly because it's not intense enough. And so there's actually now this question of, we're going to have to start to think about all this physics that I've been working on, this completely separate domain, in the domain of medical accelerators. So it's very early days with that, but we may yet see some of my research strands coming together.
Yeah. Oh, it's fascinating stuff, Susie. Now, before we let you go, I did want to talk about your book because, and we won't get into why you're in quarantine over there in the UK, presumably some sort of exposure, but you're stuck in the house. But it's good timing for you because you're going through the proofs of your book, which I believe is being released in April. Tell us a little bit about that.
Yeah, it is good timing to be stuck inside for a week. I just got contact traced, that's all. So the book is called The Matter of Everything, and the subtitle is 12 Experiments That Changed Our World. And it is a journey through 12 key experiments in the history of particle physics, my field, and how it is that we actually learn what we know about the universe on this minuscule scale, not in a theoretical sense, but in a hands-on, practical, bring it down to earth. How do you actually learn this kind of way? And that involves lots of very human struggles. There's lots of interesting characters in the book. And then it also, with every experiment that I've chosen, it also takes us through the long-term view of the impact of doing this kind of curiosity-driven research. So with every experiment, I also take us through to, well, what became of that experiment, or what became of the information that we learned, the theories that we developed, etc., as a result of that data. And what we find is this amazing story of everything from electronics to the chips inside our computers, to radiotherapy technology, to MRI, CT, and PET scanners. Basically, a whole lot of our modern technology and all the things we rely on in our modern world, a lot of them came from this fundamental curiosity-driven research, but over timescales that most of us are not used to dealing with.
Yeah. Look, it sounds fabulous, and it's due out in April. So
due out 28th of April.
28th of April, folks, you can
in all
pre-order.
Good bookstores.
All good bookstores.
Yes, all good bookstores. So that's the UK
pre-order.
and Australian launch date, and the US one will be a little later. People can pre-order, and I do highly encourage you to pre-order because that will help the book succeed in the world. And I know at least that Dimmicks in Australia have the pre-order link live already, and I'm sure lots of other retailers do as well.
Fantastic. Well, folks, have a look for that one. It's The Matter of Everything, and it's Susie Shee, and her surname is spelled Sheehy. Did I get that right, Susie? Yep, there we go. So you might want to look that one up. Susie, thanks so much for chatting to us. Now, you're back on the 8th of December, I believe.
Yeah, I leave on the 8th, and I'm doing the 17 hours in one go to Darwin. So I arrive on the 9th.
Good effort. Well, once you're back, we'll get you in the studio and we'll talk more about particle physics. But thanks so much for joining us today, and hope you get out of quarantine quick, and safe travels on the way home.
Thanks, Shane.
Triple R on FM, digital, online, and via the app.
Welcome back, everybody. You are listening to Einstein a Go-Go. I'm Dr. Shane. On the line with me now is Dr. Stefan Vervoort. He is from the Walter and Eliza Hall Institute and the Peter Mac here in Melbourne. Stefan, good morning. How are you going?
Good morning, Dr. Shane. Nice to be on the program.
Oh, look, it's great to talk to you. Now, first of all, I have to give you the hugest congratulations because you have been awarded one of the very prestigious CSL fellowships. Now, this is as I understand it, 1.25 million over, is it 5 years?
Yeah, it's over 5 years, so 250 a year, which I will use I'll be starting my lab next year at the Walter and Eliza Hall. So it's an amazing timing to be the recipient of this fellowship. Yeah.
Yeah, I guess we should clarify to people that you're not getting $250,000 in your pocket per year as part of the fellowship. This is for the research work.
Absolutely, yeah. No, this will all go to cancer research and understanding how the process called transcription works.
Yeah. Now let's get into that. Tell us, what does transcription mean? What is this process in the body?
In the simplest terms, right? So you have DNA in your cell, and that encodes all the information that we have in the same way that a library contains all the books, right?
Yep.
But in and of itself, that doesn't do anything if you're not reading the information that is within the books. And every cell contains a messenger factory. And this messenger factory copies these messages that are in the DNA, encoded in that information. And these messages really instruct how the cell should behave, right? And as you can imagine, that has to be very tightly regulated because in our body, we have different cell types. We have neurons, we have intestinal cells, and it's really how the DNA is read by this cell's messenger factory that determines the identity of the cell. And when this goes wrong, right? So when the wrong messages are selected, that can invariably cause human diseases, developmental diseases, but also, of course, cancer. And that's particularly prominent in particular blood cancers where this messenger factory is perturbed. Yeah.
And is this something that, like many things as we get older, these sort of errors just turn on in some way, or is it something where I might be born with a sort of malfunction in that messenger factory that I just can't get rid of?
There are very rare cases where people are born with mutations. So I think the reason why, so generally people are understanding of mutations that's really where there is an error in the message, right?
Yep.
And what my work really focuses on is not sort of errors in the message, but maybe when wrong messages are sent at the wrong place and the wrong time. Now, I don't think that process over your aging, mutations increase with age.
Yep.
But I don't think that the machinery itself necessarily functions any poorer when you get older. But it is this dysregulation that is fundamental to cancer. Yeah. Yeah.
And do we have any feeling? I guess maybe this is part of what you're looking into, of what sort of causes this to happen suddenly at some point in our life. I mean, we see cancers in children, we see cancers in people, in the later part of their life, and it is perhaps more frequent when you're older for various reasons, but we do see it across the entire age spectrum. So do we have a feel for what's sort of turning this on, or what causes this error system to start to come into play?
Yeah, I think so what is interesting, I think with these large efforts to sequence human genomes, the DNA sequence, we've come to understand that these key players that regulate the cell's messenger factory. So it's really finely controlled. I want people to understand that this is not just an on-off switch. There's many, many regulatory points. And the proteins or the genes involved that regulate this process, they can be mutated or dysregulated in other ways. So that they might be highly expressed or turned off at the wrong point. And that can occur all throughout your normal development. And when that happens, that then can cause cancer, right? And in children, you see these recurrent breaks in the DNA that cause that. In adult patients, it might be mutations.
Yeah. And in terms of treatments, how far along are we? Because I know with blood cancers, there's been some spectacular successes there, in particular coming out of Weihai. But, we've also been hearing a lot over the last decade about CRISPR and their ability to actually, make real amendments to our DNA in ways that we couldn't do easily in the past. I mean, how is that sort of playing out with regards to these sorts of cancers and what's driving them?
So now what my work has been focusing on is we are developing, and their companies are working on this as well, very selective inhibitors that sort of target the key components that regulate this messenger factory, right? And the idea is that in cancers, when it's dysregulated, they are extra sensitive to anything that perturbs the functioning of this messenger factory. And therefore, they're exquisitely sensitive to targeting. And that we've demonstrated that you can target key components, and that has therapeutic benefit, and some of those are in clinical trials. Now, as to the CRISPR part, my work uses CRISPR Cas9 systems a lot. They haven't, I think, progressed to the point where we are using Cas9 directly to target cancers, but it has really, really allowed us to rapidly progress our understanding of disease. So in my work, we engineer specific mutations. We can now screen the whole genome. So we can make mutations in every single protein and see how it affects the cancer's growth, how it affects tumor resistance to therapies. And we have made some really groundbreaking discoveries using Cas9 CRISPR systems. Yeah. It
must be amazing having that capability now to look at, as you say, every single protein and look at how they all affect, what's going on with the cancers. I think back to, what you said earlier about this idea of targeting these specific problems. What exactly does that mean? I mean, I think people would be familiar with, there's radiotherapy where you're using radiation to treat cancer, usually when it's a tumorous sort of scenario. There's chemotherapy, which is used to treat, tumor scenarios, but also cancers that are distributed throughout the body. We've heard a lot more recently about immunotherapy, where we're, getting our immune system to start doing the job for us, which is amazing, probably where we'll be heading, I suspect, more in the future. Where does this sit in that spectrum, or is it different again?
In my opinion, immunotherapy is incredibly exciting, and my work is focused on that a little bit as well. There's some interesting interplay, actually, between immunotherapies and these cancer-specific messenger targeting. Because, I'm sort of getting distracted here, but we can also, some of these immune genes are also dysregulated by the cell's messenger factory, and we can target that using small molecule inhibitors. So there's actually interplay between them, but I see this as a completely separate type of therapy that sits next to the chemo, radio, and immunotherapies. And I think the goal over the next few years is to make it more specific for the cancer cells and less sort of targeting the normal cells in your body. That's the whole purpose of what my work will focus on, to make it more targeted or tailored towards the cancer cells.
Yeah, and I'm guessing, one of the things we should always be clear about is, this stuff has a very long tail, doesn't it, in terms of time frame. We're talking about a fairly, you mentioned one clinical trial, but we're talking about a fairly long and protracted sort of battle, if you will, in getting this to work against cancers. Are there any sort of treatments based on this sort of technology that are available now, or are we still a fair way off?
There are some that are they available now? That's a very good question, actually. We recently written a review about in Nature Cancer about targeting transcription. I think it's primarily clinical trials that are on the go to see how they can be applied, but it's very exciting. And sometimes you get these. We try to predict. That's another angle. Is we try to predict where these therapies should be applied. What type of cancer would you want to treat, right? And sometimes you get these unpredictable results where some cancers are very sensitive to a certain type of perturbation or inhibition, and that's what we're trying to understand as well. What causes that?
Yeah. Now, Stefan, before I let you go, I should ask, have you managed to get into the Weihai building as yet? I think they have researchers back in there. They've been doing well. Have you, how far away are you from setting up there? And have you even been in the building during this pandemic? Has it been able to be accessed?
Yeah, I've been going back between Peter Mac and Wehi over the last few months.
Yep.
So I'm sort of working in between at the moment, but my lab will open at the beginning of next year. So it's a really exciting time.
Yeah,
getting some work in though.
Yeah, look, fantastic, and congratulations again on getting this CSL. Fellowships, 1.25 million over 5 years. That's great. You're working at two of the most prestigious institutions in the country, if not the world, with regards to cancer research. So, and it's only a short walk between the two, which is that's kind of nice
true,
as
yeah,
well.
Yeah, exactly.
And two of the best buildings in the city. So, Stefan, thanks so much for chatting to us today. Good luck with the work once you get going there and you get your lab set up, and hopefully we'll get some amazing outcomes. Thanks so much.
Thank you very much, and good luck with the show.
Thank you. Folks, that was Dr. Stefan Vervoort from a part of the Walter and Eliza Hall Institute and the Peter Mac here in Peter Mac is the cancer hospital in the Victorian Comprehensive Cancer Centre, the big, beautiful building near the roundabout, just near the University of Melbourne there. We are going to take a break for some music, and in a moment we're heading to another part of the globe. We'll be talking to our next guest from New Zealand, all about volcanoes and lava and all the stuff that, you just loved as kids, right?
Triple R on FM, digital, online and via the app.
Welcome back, everybody. You're listening to Einstein A Go-Go. I'm Dr. Shane. We're having a huge day today of international guests. And on the line with me now all the way from New Zealand is Dr. Janine Krippner. Janine is a volcanologist and is actually part of the Smithsonian Global Volcanism Program in Washington, D.C., but she is working remotely at the moment because of the pandemic. Welcome, Janine. How are you going?
Hi, good. Thank you very much. How are you?
I'm good. Now, first of all, I want to find out from you, how did you initially get interested in, volcanoes and, this area of sort of geology? I mean, I think all of us, me included, that was the stuff in the books when we were kids that we loved, right? I mean, it's an exciting area, but there's a big difference between, I ended up in physics, so it didn't take with me. What happened that got you into volcanoes?
Oh, it's a good question. Like every other kid, I think I just loved volcanoes. I really did. And when we went down to the volcanoes south of here, I was in love with them. Like I couldn't get my eyes off them. And I was 13 years old in geography class. My teacher wrote volcanologist on the board. And I sat back in my chair and thought, that's what I am. And that was it. That was many years ago now, and I'm still following the same dream. Yeah,
that sounds fantastic. And when did you see your first volcano? Because I suppose in Australia here, I grew up not far from a place called the Organ Pipes National Park, where you can see into the lava flow from a long ago volcano here in Melbourne, and it's amazing. You can see that. I want to say hexagonal structure. You can correct me if I'm wrong.
Columnar basalt, yeah.
Yeah, which is just phenomenal. You see it and it's phenomenal. And the sort of visible access to that is amazing in this location. But in Australia, we don't have, now I'm going to get corrected here from a geologist, I know, we don't have what the common person would call an active volcano, although I know these volcanoes have had activity in the last 10,000 years, which I think classifies them as active. Anyway, you can correct me if I'm wrong, but in New Zealand it's a very different situation. I mean, how many are there in total that are active at the moment in New Zealand?
We active in an active phase of actual eruption right now. We have Whakaari White Island.
Yep.
We also have some related volcanoes up in the Kumanik Trench, but as far as New Zealand, the landmass would be White Island. We had an eruption at Ruapehu in 95, 96, and a much smaller event in 2012. And then before that, there are eruptions going back quite frequently at those volcanoes. And we have a young volcanic field in Auckland under our major city too. So I grew up surrounded by volcanoes.
Yeah. When did you see your first one? How old were you when you saw your first volcano?
Where I grew up was surrounded by extinct volcanoes, although I didn't know that when I was a little kid. So in my eyes, I grew up around them. But I was pretty young when we went down south to see the more active ones, not actually erupting, but we could see the ash plume from Ruapehu in 95, 96 from here.
Wow.
So pretty young.
Yeah. And when was the first time you got to see lava, sort of, actual lava flowing, red, glowing, the stuff that we all see the pictures of and go, wow. Like, how old were you when you first saw that?
I haven't seen a lava flow at a volcano yet. I studied the more explosive stuff, but I have seen a lava flow that was man-made in a lab for experiments. and that was in 2012, I think. So I've seen lava, but not coming out of a volcano yet.
Yeah. I mean, that's probably, in some sense, that's probably a good thing, because it means you haven't been within the proximity of a volcano that's that active, which is,
Well,
yeah.
I've been on very active volcanoes, but not, the more explosive kind. So ash plumes, not lava flows.
Yeah. And in terms of one of the things that I suppose is important for people to get their head around is just what is sort of correct information around volcanoes and what is misinformation. And we see the news reports and they give us some fancy photos, which I got to say I love. It's amazing stuff to look at, like nature in all its glory. It's phenomenal. But the information around volcanoes, because it has such an impact on people's risk assessments and the way in which they go about their business, and of course we saw in 2019 the White Island, sort of activity there leading to, as I recall, I think it was 47 people that were hurt and 22 or so died. I mean, this was quite an extraordinary scenario. So there's a lot of really important risk assessments being made. But, what sort of misinformation are you coming across around the world with regards to volcanoes? I mean, I'm guessing this is part of your program in Washington.
Oh, it's so much. And misinformation is more like the communication stuff I do is more outside of my job. Something I'm not doing anymore, but I was doing in my job was writing up volcano eruption reports. So I saw a lot of misinformation there too, but just generally it's everywhere. There's misunderstandings, blatant misinformation on every aspect of volcanoes. And it is a real problem because everything's online now. So you might say, well, these people in the UK are posting this about a volcano in Indonesia. It doesn't matter. Well, no, the people in Indonesia who might be impacted by this and need to make potentially life-saving decisions can see this information now. And we know that false information travels much faster and further on the internet than any facts because volcanoes are pretty spectacular by themselves. I don't know why people need to make things up. But that's the way it is. So it's really bad. And those of us who are speaking about what's actually happening is so outnumbered.
Yeah. Can you give us an example of the sort of misinformation that you're seeing?
Yeah, so I think we've all seen the La Palma eruption in the Canary Islands that has been going on for the last, months. Nearly 2 months now. Yeah. So what is time anymore? There was a study done which has been since re-looked into by multiple researchers and proven that it's not an accurate study at all, talking about a mega tsunami. So talking about a massive chunk of the volcano or the island sliding off into the sea and causing a tsunami along Eastern Americas. So all the way down to the bottom of South America, all the way up to the top of the United States. And that, unfortunately, because that's such a flashy topic, a BBC documentary was also done on that paper, which has since been refuted. And so a lot of us have been getting messages from terrified, and I don't use that word lightly, terrified people in the United States and South America, Central America, just petrified that they're going to get wiped out by a mega tsunami because of this relatively small eruption. So that's something that's really impacting people's lives. We're all living in a pandemic. People don't need this additional fear. Yeah, it's really heartbreaking.
Yeah, it's interesting to me because the sort of information with regards to volcanoes and eruptions would be, especially for the people nearby, would be important on a daily basis. I mean, I'm assuming just as we have when there's a flood, there's information on the direction and expectations of floodwaters and where they're going to hit and when. I mean, we have this a lot in Australia, and to be frank, the Bureau of Meteorology and other groups are really good at distributing that information to various towns and so forth. You have a similar thing with regards to lava flows and ash and all those things, and presumably locals do not need that information being distributed by those who are not on the ground or not in the know as to what's actually happening, because it might cause you to go in the wrong direction, right?
Yeah, it's interesting. It depends on where. So in the Canary Islands, I actually asked some of the local volcanologists there if they're having a lot of trouble with people asking about the mega tsunami, and their answer was no, we've got much bigger problems here. But so if you have a community that has a good relationship with their officials and they know where to get information from, then that works well. But if that's getting muddied up by the misinformation out there, that's when trust can start to wear down. But there's the other scenario where, for example, Bali in Indonesia, which is a highly, as a lot of Australians know, it's a huge tourism hub.
Yep.
So you might have a lot of people in some of those areas that don't know who the officials are. So in that case, they're going to be getting their information from different sources online. Yeah. And a lot of us now go to social media when we want information. And that's, unfortunately, it can be one of the worst places to go, especially YouTube. Don't go to YouTube. Yeah. I have a YouTube channel on there, but don't go to YouTube.
Yeah, it's interesting when you talk about that sort of lack of knowledge that locals have in other places and so forth. I know, recently we had a magnitude 6 earthquake here just outside of Melbourne, a couple of hours out of Melbourne in New Mansfield. And, for most people in Melbourne, it was like, sorry, what's this? We don't get those sorts of earthquakes in Melbourne. So in a sense, we're like a whole lot of tourists who'd gone to Japan or, somewhere where they're more common. And we just really didn't know, what was up and down. And for many people, I think, I noticed there was one wall collapse on some side of one building in Melbourne as a result of this. And I think I saw this image of this wall from like 25 different angles because we had to show something, because otherwise there was really nothing, that we could show in terms of damage from this earthquake, because there was no damage. And, we have that sort of mindset whenever we go to foreign countries that everything's sort of taken care of. But I remember the first time I went to San Francisco and stayed with a colleague, and he gave me like this 20-minute sermon on what to do if there was an earthquake. And coming from Melbourne, it was really valuable because I really didn't have that information. And I'm guessing, in many of these cases, it's a similar thing where people just, people want to go to these places because they're spectacular. Part of that is because of this activity that's happening in geological terms. But the dangers are just outside our realm of understanding and experience, aren't they?
Yeah, definitely. It's amazing when it comes down to it. Like, we all know what a volcano is. A volcano is something that we see in everything from movies to cartoons to on the news to in documentaries. So volcano is part of our vocabulary, right? 2 years ago, how many of us knew what an epidemiologist was?
Yeah. Yep.
So it's one of these fields of rare-ish fields of science where we all have some sort of connection to it. Like, oh, I've seen a volcano in there. Oh, I thought those were so cool when I was a kid. So there's this huge awareness of them. But when it comes to the really important things, like what is volcanic ash? What is the difference between a lava flow and a pyroclastic flow? The knowledge there is dangerously low.
Yeah.
I found when Kilauea was erupting, we were watching the lava flows in 2018, which were devastating for the local communities. And then at the same time, there was a large eruption that produced a pyroclastic flow at Fuego in Guatemala. Now, what a pyroclastic flow is it's a very fast-moving avalanche, essentially, of hot rock, volcanic ash, which is pulverized rock and glass and crystals, and hot gas. So it killed many, many, many people. It went through several villages. Really devastating situation as well. But I found myself talking to a lot of people about the difference between these two very different processes. And that was one of the many times I've sat back and thought, oh, wow, the knowledge about volcanoes is so much lower than you'd think.
Yeah. It's interesting because one of the things I've often said is just because people know the word for something doesn't mean they have solid understanding. And a great example of that is the term DNA. It's thrown around like everyone understands it these days, but in reality, actually, that's not the case. And we have to be really careful when we're communicating science to acknowledge that just because there's familiarity with a word doesn't mean there's understanding. You must see that a lot, especially with terms like, volcano. Pyroclastic flows, I suspect fewer people know, but you must come across that a lot.
Yeah, I really do. It's, when you have an eruption, especially one that's has a decent run-up time. So before a volcano erupts, it gives us signals. So it gives us earthquakes. It releases different gases from the magma. A lot of gas comes out of magma when it's rising. There might be deformation. It might actually cause the ground to physically move, even though it might be so small we can't see it. We can measure this stuff. And there's all these signals a volcano can give us. Now, that lead-up time can vary significantly. It might be hours, it might be days, it might be weeks, it might be months. For your listeners who remember the Argung eruption in late 2017, that was 2 months. So then when you have these huge run-up areas, you get people looking at these graphs put out by the Volcano Observatory that gives simply the number of earthquakes. It doesn't tell you anything about depth or size or type or what that means. And then you get people giving out predictions.
Yep.
And it's not, the more you know about something, the more you don't know, right? It's the case with everything. So once you know a little bit, you think you know a lot more than you do. And the more that you know, the less confident you are.
It's interesting when you mention some of those parameters that we can measure. How do you determine whether or not there's going to be an eruption? Because I can imagine if you have something like Mount St. Helens where, there was significant change in shape and so forth, I guess it's hard to predict exactly when, but, something was happening there with this particular mountain. It was changing quite significantly over a relatively short period of time. But how do you go, like with something like La Palma and some of the other volcanoes? I mean, how do you know, first of all, that this scenario that's happening now was going to occur? But second, what's going to happen next? Do we have an understanding of where this will go?
Oh, that's a really good couple of questions there. So so I don't predict volcanoes. A prediction would be saying there's going to be an eruption on this day and it might be this size or it might be this specific location. What we do is forecasting. So it's really important for people who are more geology-based volcanologists like myself who go out and look at the rocks and say, this is what this volcano has done in the past. That involves, even in itself, geochemistry, so looking at the chemistry of the rocks, the crystals, the trapped bubbles in it, what the rocks look like and what they tell us, so we can look back. I mean, some people look back millions of years to see what a volcano did. I tend to work on the much younger things, but we can do that. So once you know what a volcano has done in the past, which is a key, and if you don't know, you need to figure that out pretty quickly. Then there's a whole team of volcanologists, usually at a volcano observatory, or a team that goes in to help as well. And they can be assisted by other volcanologists at universities or other observatories too. It's a really interdisciplinary team, field that works as a team. So we have geophysicists that look at earthquakes. That's like, I go to a geophysics talk at a conference. They're talking about something as simple as earthquakes. I do not understand what they're saying. It is that technical and that specialized. And then you have the gas team or the gas people, and they're looking at the different kinds of gases, the amounts of gases. You might have remote sensing people using satellites. And of course, there's the technicalities of all of the instruments detecting these things. Deformation, so the movement of the ground, that's geophysics again. You can be looking at the fluids around the volcano. Is there a crater lake? Are there hot springs coming out of it? So there are so many different signals that need to be interpreted by specialists in that specific thing, and all of that put together. So the more information you get, the clearer image you might have of how much magma can be rising. So if you're getting a lot of deformation, a lot of gases being released, a lot of earthquakes of specific kinds, that helps you narrow down what kind of eruption you might have. But the important thing is there's a lot of success stories about when volcanologists have understood that something might happen, have evacuated people and saved lives. So it does work. It is complicated. It is hard, but we're a global field working together to understand these things.
Yeah, I suppose it's, we'll take a break in a moment, but it's always that scenario too where people get pretty annoyed with you when you give them a false sort of positive and you evacuate them and it wasn't needed. But as we say, on those occasions where it actually is, it's forecasting, it's not a perfect science, it's forecasting. People don't get as annoyed these days when the weather's out by a few degrees, but it's a similar scenario. You can't be definite about it, and in this case, it's saving lives. So, if we have a few false positives, then so be it. It's not the worst thing in the world. It's a lot worse than us not knowing at all. So now we're going to take a quick break here. Happy to stick around for a little bit longer, Janine. Excellent.
Absolutely.
We will have some important station announcements for you folks, and we'll be back in just a few moments to learn a little bit more about volcanoes and lava.
Triple R on FM, digital, online and via the app.
Welcome back, everybody. We are speaking with Dr. Janine Krippner from the Smithsonian Global Volcanism Program, currently hibernating in New Zealand due to the pandemic. Now, Janine, we've talked a lot about volcanoes. One of the things we haven't dived into a lot, though, is lava being this amazing scenario. I mean, just give us the sort of the quick version of, where does lava come from and what does it do in terms of release of pressures and so forth for volcanoes? I mean, why do we get it?
Lava is amazing, isn't it? Like, if you think of holding a rock in your hand, we've all picked up a rock in our lifetime. If you think of how hot something must get to melt a rock, is amazing. So lava or magma, when it's below the surface, it's lava once it's at the surface. It actually forms at multiple depths below the crust, or within the crust, below the crust, depending on the location, the chemistry of the rocks that are melting, the particular type of zone, so a subduction zone like we have here in New Zealand, or if we have a hotspot like Hawaii, or we have rifting like the East African Rift. So the tectonics is really important as well. So the magma can form way down below the crust, so tens, hundreds of kilometers, and then slowly make its way up. And it's changing as it's going. So it might pause for a few hundred years, and we call it evolving, the magma evolving. It might turn into a magma that could be a lot more explosive and dangerous. So magma is essentially melted rock. When it's below depth, it's usually got a lot of crystals within it, a lot of solid stuff. Once you get enough liquid melt together, that's when you can start leading to an eruption. So it starts to rise because it's more buoyant. It's less dense. It is buoyant within the crust. And then you get to a certain point where it's kind of shallow, where gases start coming out. And we can detect that, thankfully. It's a bit of a nod that there's magma down there. Oh, gosh, I'm getting confused with lava and magma words now. But, yeah, you're essentially, when it gets close to the surface, that's when pressure can be a bit of an important point. So if you have gases coming out of the magma and forming bubbles and they can't escape, once it reaches the right conditions at the surface, that can release an explosive eruption, depending on the magma type. So basically the answer to everything is it depends. And it's complicated, but it's melted rock, which is amazing. It's extremely hot. If you stand close to it, you'll actually get a sunburn from the radiative energy. It's painful to be near. That's just how hot this stuff is. So we're talking, the cooler lavas are around 800 degrees. The hotter lavas are around 1200.
Wow. Yeah, that's hot stuff. Now, with this stuff, like as you said, like there's so much different material in lava. I assume that affects the way it flows, because we see some of these images where it looks like a torrent river kind of scenario, and others where you kind of could walk backwards and just say, you can't get me, I'm faster than you. Is that right? Is it all dependent? I'm assuming that's not so much temperature, but composition that really changes the flow characteristics.
Yeah, it's actually an intermix between the two. So the chemistry of the melt and where it's coming from and how fast it rises, also like how much gas it has. There are so many different properties which affect how it flows, or what we call the rheology of lava. And that's not my specialty. That's the specialty within itself. There's physics that goes into modeling lava flows. But if you have a really hot flow that is also a runny type of lava, once it's at the surface, you're going to get these really fast moving flows. Now, they do cool down pretty quickly, but if you get a tube forming or a tunnel, a large tube forming, it can actually keep it insulated, like putting a jacket on in a winter's day, keeping it hot, and it can go for many, many, many kilometers away. So the longer it can stay hot, the longer it'll stay running, the further it can go. Once it starts cooling down, that's when we can get these really slow-moving things. But some of them do come out of the vent cooler and thicker and just form these really thick, slow-moving lava flows. And we're seeing those at La Palma as well. Yeah.
Oh, look, it's amazing stuff, Janine. You have a super cool job. I always wished I'd grow up to be a volcanologist. Never did. But,
you still can.
Well, never too old. Maybe a little bit, but it's cool stuff. But I vow to see lava before you. That will be that will happen. I'm going to go to Hawaii or something and just see if I can find it. But thank you so much for chatting to us today. You're doing great work. When did you get back to Washington?
I'm actually in New Zealand for good now. The pandemic forced me home, but I'm really happy to be here. So
excellent. Well, that sounds great.
I'm home.
That sounds great. Well, thanks again for chatting to us. Good luck with the ongoing work, and we will hopefully chat again sometime in the future.
Thank you. I'd like that.
Folks, that was Dr. Janine Krippner from the Smithsonian Global Volcanism Program and currently based in New Zealand. You've been listening to Einstein a Go-Go. I'm Dr. Shane. Remember, science is everywhere, and we will come back to you again next week with another hour of science. Have a great day. Hi, this is Dr. Shane. Thanks for listening to the podcast of Triple R's Einstein a Go-Go, a weekly radio show exploring the wonders of science and its impact on the world. Broadcast live on Triple R from Melbourne, Australia, every Sunday. Hope you enjoyed the podcast, and feel free to get in touch with us via Einstein a Go-Go's Twitter account or Facebook page.